Good morning and welcome back. Before we start, I would like to talk about a very important issue that is our midterm exam. So this is the IMSL. Yesterday, I sent you this information. Let me read it for you. Dear all, long time no see. How are you doing? Many students care about the midterm exam. That is a good news. That's good things. The midterm exam covers chapters 8 and 9 and will take 40% of the final grade. 40%. And the midterm exam will be open book. That is, you can discuss with your friend. You can use Google. You can use any software you want. I will upload the questions to ILMS on April 28th. And I will provide the standard answer sheet. And the standard answer sheet will be provided in front of room 118 of the physics building. Write your answers in the answer sheet so that we can evaluate your paper correctly. Please return your answer sheet by noon, 12 o'clock of May 4th. A box will be placed in front of room 417 to collect your answer sheet. If you are not in Taiwan, for example, for students from mainland China, you can send your answer in PDF to me through email. Late papers will not be considered for grading. Okay, that's very important, so pay attention to this one. Late papers. I give you 7 days, or not seven, close to 7 days to write your answer. So you have sufficient time to write your answer after the quantum mechanics midterm exam, right? Okay. Okay. So many students care about this one. That's the first announcement. Second, today we will talk about chapter 10, about scattering and diffractions. Diffraction and scattering. That's very interesting. Let's the following chapters of chapter 9. In chapter 9, we talk about dipole radiations. Radiations from electric dipole and magnetic dipoles. And now I will show you how to excite the dipoles. And the dipole, electric and dipole could be from scatterer, from material, from molecular, from atom, from many materials. Okay? And we will consider the scattering at long wavelength conditions. Long wavelengths, very long. That is lambda is greater than the dimension of the object. Okay? What is the long wavelength? Long wavelengths, the lambda will induce electric dipole and magnetic dipole. How about for short wavelengths? Just imagine you have a flashlight and the flashlight just shine on you and you will see your shadow. So scattering is not very obvious, not an obvious effect. So in that case, scattering is uh, not very clear. So if we want to have a clear scattering effect, lambda should be greater than the physical dimension. Okay, so let's consider differential scattering cross section. The major difficulty of this section is we will define many things. Many, for example, we have an incident wave, incident wave from these directions. So the direction of the incident wave will be n0. Incident wave E, boldface E with subscript INC, incident. H with subscript INC. Okay, we have E and H. That's the material here. And this one, E field will induce electric dipole. H field will induce magnetic dipole. Electric dipole and magnetic dipole, P and M, will generate radiations. For example, if a detector is here, observer is here, and then the signal will propagate to here. So E with XC scattering or scattered. SCH here is scattered electric field and scattered H field. And we have observer here. Okay? And this is the angle between incident wave and observer. So this figure is quite important. Look at this word, scatterer. It means scatter, E-R-E-R. So it's correct. Scatterer means the object that will scatter the signal. That's scatterer, 散射物 in Chinese. Okay. In chapter 9, we consider vector potential. And from the vector potential, we can calculate H field. And with the H field, we can calculate E field. That's in chapter 9. But for many cases, we prefer to write E field first. And from E field, we know it's correlated to H field. Okay? Through these relations. So you have two expressions. The first expression is express H field equals curl of A, and then E field equals Z0 times N cross H. Okay, that's in chapter 9. But in chapter 10, we prefer to use a different strategy. That is, write E field first, and then from E field we can easily calculate H field. Z0 is the characteristic impedance. Let me write it down. Z0 equals square root mu 0 over epsilon 0. That's the ratio between mu 0 and epsilon 0. And the incident wave is incident from free space. This is material here. Others, nothing. So it's mu 0. Otherwise, okay? You might be confused about a notation. Epsilon 0. What is epsilon 0 boldface? Once again, we use epsilon 0 to express the polarization. It can be linearly polarized or elliptically polarized. It can be real, just like in the x direction or in the y direction, all in the z direction. Okay, and normally we prefer this direction is in the z direction, so we can simplify the calculation a lot. And so epsilon 0 can be real or can be a linear combination of two polarization and become a circularly polarized wave, such as Ex epsilon x plus minus I epsilon y. So this plus express the positive helical helicity. Minus means the negative helicity. Okay, so epsilon both face epsilon 0 plus minus just indicate it's a circularly polarized. Yeah, so don't be confused with here. Okay, it's the free space. We already assume g0 equals square root mu 0 epsilon 0 here. Maybe I should use eraser. Okay, and okay, we have explained the notation so far. So E incident and H incident will induce multiples on the object. This is the object, which in turn generate scattered radiation. Incident wave and length generate P and P and M will generate radiation in all the direction. In all the directions. Since it will generate in all direction, in this direction, in this direction, in this direction, so we say it's differential. Okay. For lambda greater than d, okay, the same conditions, same conditions. Only the induced P and M are important. Higher order terms, higher order multiples are not very important. In that case, all we need to do is P and M only. Okay? Remember in chapter 9, 9.19, equation 9.36, we have these relations. We have H due to P, H due to M, and they have a simple relation. Z0 HP cross N, Z0 HM cross N. Okay? Now we will write into this form. Okay? To do that, all we need to do is substitute H into here. So we got K squared here, the same, over 4 pi, the same, N cross P, N cross P cross N, okay, the same. Exponential IKR over R, the same. The major difference is we have a C here, we have Z0 here. What is C? C is the square root epsilon 0 mu 0, right? C is the speed of light. C times Z0. So we have a cancel. This is numerator, denominator. So eventually C dot Z0, we got 1 over epsilon 0. This one. Okay? So the first one is correct. The first term is correct. How about the second term? Second term is substitute this one into here. N cross M cross N. N cross M cross N cross N. Wow. We can use this vector product, triple vector product identity. A cross B cross C equals A dot C times B minus A dot B times C. Okay? So N cross M cross N cross N equals, let's switch the order, minus N cross M cross N, and the first terms equals A dot B times C. The first terms, okay? Let's consider this term first. We have a minus sign, A dot C times N plus N cross M. Okay, these terms will operate cross N again. So nothing. N cross N give us nothing. And this one, N dot N, N is a unit vector. Unit vector, just to indicate the incident, the direction of the propagation. Okay, so N dot M, N cross N 0. So we got only one terms left, M cross N. Okay, M cross N. Switch the order, minus N cross M. Okay, bingo. And the coefficient, the same. K squared, the same. 4 pi, the same. But this time, we do not have Z0 only. So we use a C here. And in order to extract a epsilon 0 here, we express a C here. Okay, divided by C. And H easy. H easy. H cross N. Oh, okay. H field equals N cross E S C divided by Z0. Okay? So this one is, we have two expressions. That's the expression in chapter 9. That's the expression in chapter 10. Which one you like? Uh, two expression. And we will use vector identity. Okay? Hence, to find ESC and HSC, we need to find the induced P and M. Okay? You can use this one or this one. Either this one or this one. Up to you. Not much difference. But in chapter, we will start with electric dipole. So we will start with this one. Okay? And later, we will use a conducting sphere. Dielectric sphere first. And then we will consider a conducting sphere. Two cases. Next page. For scattering problems, a useful figure of merit. Figure is 指数, 数字. Merit is 公积，可以说是一个指标 ，an index. To express its good or not. To express its properties. So figure of merit is the scattered power relative to the incident power. Incident power relative to the scattered power. That's a figure of merit. But how to collect the scattered power? That's not that easy. So we don't use that. On the other hand, it's also important to know the polarization state, the status of the polarization of the scattered radiation. If the incident is linearly polarized and scattered is linearly polarized or elliptically polarized, that's the questions. Okay? If the incident wave is circularly polarized and the scattered wave is also circularly polarized, but at different position, you might detect different signal, different polarization. Last, we will define a differential cross-section. Let's differential cross-section. The dimension is cross-section, m squared. The dimension is m squared. It's defined as the sigma over the omega. The omega is the solid angle. Normally, we use omega to express the solid angle. Is the observer, is the incident wave direction. Polarization, epsilon, to be determined. Incident signal, epsilon, given, to be determined. So it depends on the direction, depends on the angle, and depends on the polarization. Let's call differential scattering cross-section. Radiated power in the n direction, radiated power in the n direction with epsilon polarization. Epsilon polarization is not drawn in this figure. Per unit solid angle. Unit solid angle. This angle. That's the unit solid angle. Okay? And the incident power in n0 direction with epsilon 0 polarization. In n0 polarization. Unit area. Per unit area. Okay? So radiated power, incident power, okay, just like a figure of Mary, but in n direction with epsilon polarization, n0 direction with epsilon 0 polarization. And so these two, eventually, this is the denominator and this will be a numerator. So the dimension will be meter square, the area, so it's meter square. Okay, you can see here, we have power in the epsilon direction that times the scattered, and incident wave in the epsilon 0 direction times the incident wave. Because it is in a free space, so the proportional constant is 1 over 2z0. 1 over 2z0. And this will r square, dimension the same. So eventually we got an r square dimension. The meaning of sigma will become clear very soon. Very soon. So for a circularly polarized state, epsilon can be written as this one. So this one just expresses the circularly polarized state. And epsilon 1 and epsilon 2 are perpendicular. So we will say that epsilon 1 might be x coordinate, epsilon 2 might be y coordinate. But for our convenience, we won't use that, because later epsilon 1 will be a different, epsilon 2 will be equals to y coordinate, but epsilon 1 is not. Okay, ey, and not necessarily be ex. That's why we use a spatial symbol. So we have to pay the price. The price is we use epsilon extensively. Let's second, be careful. Epsilon 0 and epsilon 0 star perpendicular to N0. N0, so the polarization is perpendicular. So it's an ideal, simple plane wave. And once again, epsilon star and epsilon is also perpendicular. So it's far wrong, far wrong. Therefore, it's a plane wave. Polarization is perpendicular to the incident wave. That's for our convenience. And epsilon 0 dot epsilon 0 complex conjugate equals 1. Normalize. Epsilon dot epsilon complex conjugate equals 1. Once again, normalize. Epsilon is not necessarily the direction of ESC. Not necessarily. Okay. You can define the direction or coordinate you want. Epsilon star dot E star gives the E components. The scattered field, the scattered electric field in the epsilon directions. I will give you a more detailed analysis. Okay, so from these directions, from these definitions, let me write it again. The sigma over the omega is a function of the scattered signal and incident signal. So just write it down, just this form. And then substituting E incident is a simple plane wave. E scattered is here. That's the induced N cross P cross N minus N cross M divided by C. C is the speed of light. So differential coefficients. This one is simple. This one times this one will be E0. Very simple. We like it very much. And we have k squared, k to the fourth, k to the fourth. And this one cancel. So we have r squared divided by r squared cancel. And we have 4 pi epsilon 0 square. Okay, so correct. So all we have is here epsilon star dot n cross p cross n minus epsilon star dot n cross m over c. Okay, so we can simplify the notation into this one. Of course, n and p and m is proportional to the incident wave. P is proportional to E field, and M is proportional to H field. But H field is proportional to E field, so they are correlated. Let me write it again. This is a triple product, so we can use the triple product again. So this one becomes P times N dot P. So N complex conjugate dot N dot epsilon star give us 0. This is the scattered observer's position, and the polarization is perpendicular to this one. We talk about this one in previous slide. So this one is 0. Good. Only one turn left. We like this one very much. Okay. Epsilon star dot p plus we just change the order. Epsilon star dot n cross m. We just change the order. N cross A n cross m, B cross c. So here we just change the order. N cross m. That's B. Change the order. Epsilon cross n. Okay, let's change the order. So we got a positive here. So eventually, the differential coefficient, differential cross-section is defined in this way. In k to the fourth divided by 4 pi epsilon E0 squared and absolute value of these two. That's equation 10 to the 10.4. Okay, let's move on. So we will consider the simplest case. No magnetic dipole, just electric dipole. So we have example 1, scattering by a small uniform dielectric sphere with mu equals mu 0. And here, epsilon r equals epsilon divided by epsilon 0. Okay? For example, if this is a Teflon here, then epsilon r will be 2.1. Okay? Just give you an idea. If this is alumina, 陶瓷, epsilon r is about 9. Okay? It's a fused quartz, 石英, epsilon is about 4.0. Okay? So lucky we have mu equals mu 0. No magnetic dipole. All we need to do is electric dipole. How to calculate the electric dipole? We can use the knowledge in chapter 4, equation 4.56. We obtain the electric dipole moment P induced on the scatterer by E incident. Okay, so P is 4 pi epsilon 0, epsilon r minus 1, epsilon r plus 2 times A cubed times E incident. And incident is given. Okay, so it's proportional to the volume of the sphere, and proportional to, not proportional, is epsilon r minus 1, epsilon r plus 2. So if epsilon r is 1, we got nothing. Okay, no scattering effect. But now we have epsilon r is greater than 1. Substituting 10.5, we just substitute this one into this equation. We got P, and know this equals 0 by assumption. Okay, so we have only one term left. Great. This one cancel out. A to the 6, a to the power of 6. So a to the 6 to the 6th power. Okay, k to the 4th, k to the 4th power. Okay, and epsilon r minus 1, epsilon r plus 2 square. And importantly, this one is proportional to, this one is epsilon complex conjugate dot epsilon 0. Oh, so differential cross section becomes very simple. Proportional to k to the 4th and a to the 6th. Okay, and proportional to this one square, and also depends on this one. So such a complicated definition of differential cross section becomes a very simple one. Therefore, we like it very much. Here is the question. 4.56 is derived from a dielectric sphere in a static field. But here it's an AC field, but still correct. Why? You can consider this one as extra bonus and send me your answer through email. Okay, you got 1 point from here. You can answer. You can send me anything you want regarding to the course material. Okay, that's class participation. So you can send me anything you think is related to the course, and you got 1 point or greater than 1 point if the answer is correct. If your analysis is correct. Okay, so next page. Okay, uh, that's how we calculate this one. A dielectric sphere is placed in a uniform electric field. It's just a reminder to help you derive this equation again. We use electrostatic and we use Laplace equations. Okay, so I will skip the following slide. You should study by yourself. Okay, how we derive these equations. We have a abbreviation CF dot. That means refer the reader to other materials to make a comparison with the topic being discussed. So you can compare equation 4.10 with this one, equation 4.54. Just a comparison. And then by comparison, you know the dipole, the electric dipole will be this one. Proportional to electric field, proportional to the volume, and epsilon zero, as well as this one. So this by comparing the result, by make a comparison with the topic being discussed, you know the electric dipole will be this one. Okay. Now let's come back to here again. We define so we have a very simple result here. Okay, so next step, we will define epsilon star and epsilon zero to give you a clear understanding about these two vectors. Okay, so we define n minus n dash n0 plane as the scattering plane. That is, the incident wave is in the z direction. Okay, let n0 be along the z-axis, and n is the observer. Observer lies on the xz plane. XZ plane. That's the definition. We prefer n0 in the z direction and observer in the xz plane. So the angle between the observer and the incident wave will be theta. Okay, that will simplify the notation, simplify the calculation. And this is the s direction. So x, y direction is here, and z direction is here. Okay. Then the orientations theta and phi of the unit vector. This is the theta, and the phi is here. Phi is the angle from x-axis. Phi is lying on a projection on the xy plane. Phi is the angle between x-axis and the incident polarization, epsilon zero. And epsilon zero is in the s y plane. Epsilon 0 just lines on lines on the x y plane. Why? Because it must be perpendicular to the incident wave. So that's only possibility. Just lines on the xy plane. So in this case, it could be in here, it could be here, but keep this in mind. The angle in the theta is pi over 2. And phi 0 is the polarization of the incident wave can be described in phi 0. Okay? And epsilon 1, just epsilon 1 is difficult to define. Epsilon 1 should be perpendicular to n. And we can easily, since n is in a x z plane, so we can define epsilon 2 to be y-axis. So this one must be perpendicular to n. Of course, n is in the x z plane, must be perpendicular to epsilon 2, y direction. So that we should define this one first. And then we know epsilon 2 linearly polarized. Epsilon 1, we can define it will be another one perpendicular to this one. That's easy. We just assume epsilon 1 is in the xy plane. Okay, so phi will be 0. And because epsilon 1 is perpendicular to n, so the angle between this one and this one, the angle between this one must be pi over 2. Pi over 2 plus theta. This n is lying on the theta. Okay, so by doing so, we can define the first one is the polarization of the incident wave and the polarization state of the scattered wave. Polarization state of the scattered wave. And this case is parallel to the scattering plane. This is scattering plane SZ plane, and this polarization happen to be in the XZ plane. Okay, and this is another plane. This plane is polarization state of the scattered wave perpendicular to the scattering plane. Scattering plane is XZ plane. The notation, the definition here is difficult. It's not easy for you to understand in class. So if we use, now we use YouTube. So you can study this one over and over again at any place you want. So you can review, you can study over and over again. It will be very helpful. So epsilon 0 is on the xy plane, epsilon 0 on the xy plane, making an angle phi 0 with the x-axis. Epsilon 1 is on the xz plane, and epsilon 2 is on the y-axis and is perpendicular to the xz plane. And n epsilon 1, epsilon 2 are mutually orthogonal. So that's why we use this notation, not use x direction, y direction, because we want to define another coordinate, another directions, another unit vectors. Okay, that will be much convenient. Mutually orthogonal, perpendicular to this one. This one, epsilon 1 perpendicular to epsilon 2, and epsilon 2 perpendicular to n. Okay, just imagine it's a 3-dimension, so you need some imaginations. Polarization state epsilon 1, epsilon 2 of the scattered wave are all assumed to be real, representing the linear polarization. Okay, so we can rewrite the notation again, applying equation 1 in chapter 3 of lecture notes. We know cosine gamma is the angle, the separation angle. Okay, so cosine gamma is the angle between theta phi and theta prime phi prime. Sine theta prime times cosine phi minus phi prime plus cosine theta prime. And so we can write, now we have 3 directions. Epsilon 0 on the xy plane denoted as pi over 2 phi 0. Epsilon 1 denoted by is on the xz plane, okay, pi over 2 plus theta 0. And epsilon 2 is on the y-axis, exactly on y-axis. So theta is pi over 2, phi is pi over 2, okay? So we can express the calculation epsilon 1 dot epsilon 0. Why? Because we already know equation 10.6. Now epsilon can be divided into 2 parts, epsilon 1 and epsilon 2. Epsilon 1 is parallel, epsilon 2 is perpendicular. Okay? So we just divide it into 2 parts. Parallel to the plane of, how to do that? Parallel to the scattering plane and perpendicular to the scattering plane. So by doing so, we just substitute everything into here. Sine pi over 2 plus theta sine pi cosine 0 minus phi 0. So eventually we got this relation. The angle will be cosine phi 0 cosine theta. Okay. On the other hand, epsilon 2 epsilon 0, simple. Okay. Very simple. Okay. Just sine phi 0. Okay. Sine phi 0. Very simple. So we don't have to worry too much. We can simplify this notation into here. Wow, very convenient. A very complicated notation can be simplified into this one. That's why we like this notation. But we have to pay the price. The price is the definition of n0, definition of epsilon 0, epsilon 1, epsilon 2. In here, epsilon 0 just represents the linear polarization, linearly polarized, okay? And we have phi 0. So later on, we will allow the phi 0 to be changed from 0 to 2 pi. That means the linearly polarization can be in any directions, or randomly polarized, okay? So we have a simple relations. Good, convenient, very convenient. So next step, we will allow the phi 0 to be random. So this is the direction of propagation. The incident wave is a fixed directions. But if the incident wave is unpolarized, like the radiation of the sun, then yeah, this direction is the same, but it can polarize in the xy plane. So we will take the time angle average and divide it by 2 pi. So by doing so, we got a simpler coefficient do not change. just average over 50. Okay, and once again, perpendicular cross section average over 50. We got this one. The same operations. So we will define another notation called pi. Pi theta. Theta is the observer's angle, the angle between the incident wave and the observer. Okay, so we just write pi theta as define the pi theta as the degree of polarization of the scattered polarization. What will we have? We perpendicular minus perpendicular cross section minus parallel cross section, and perpendicular plus parallel cross section. So obviously this one will be 1. And this is the difference. So just express the perpendicular polarization minus the parallel polarization. So the result will be simple, just sine square theta, because here is 1 minus cosine theta, 1 plus cosine theta. So the maximum value is 1. Okay, okay. So the theta equals total cross section equals the sum of these two. The theta perform the 30 angle. We got the omega perform the 30 angle. The incident wave time average and total angle. Just average all the 30 angle. The incident wave in the z direction and 0 direction. But observer can integrate all the space, all the angle, x theta direction and phi direction. So we got this one. Eventually, just average over everything. All the angle, 2 pi, give us 2 pi. And this one give us another 1 plus cosine squared theta. And from 0 to pi. And eventually we got this one. K4, k to the fourth, a to the fourth, and a squared. So obviously Ka is long wavelength limit. So this one is not very big. And k fourth to a k to the fourth, a to the fourth. So obviously this one will much smaller than pi a square. Pi a square is the cross section of the sphere, of the dielectric sphere. But here, under the long wavelength limit, is much smaller than pi a square. Okay, that means we have a sphere of radius a cross section pi a square, but under long wavelength limit, its effective cross section is much smaller than this one. Okay, extra bonus again in this equation. Why add powers instead of adding fields? Okay, remember we want to calculate the total scattered power divided by total incident power. The higher the better. Okay, last page. This one gives sigma phi 0 smaller than pi a square, implies that only a small fraction of the radiation incident on the dielectric sphere is scattered. This is true even if the scatterer is a perfect conducting sphere. Even if it's a perfect conducting sphere. You put a perfect conducting sphere just on the sunlight, you see the area is clear because it's short wavelength limit. However, under the long wavelength limit, it's different. Okay, so next time I will show you scattering by a small perfect conducting sphere. This conducting sphere will induce both electric dipole and magnetic dipole, and they will have different effect. So next time we will talk about these issues. Okay, I will stop here. See you next time.